This video looks at time-like and null curves and their connection with causally related events. It deals with time-like, light-like and space-like space-time intervals and uses these to classify vectors and curves. It also deals with past and future light cones and how to tell if a curve is future or past directed. Alright, so we have our Minkowski space-time diagram, albeit empty at the moment. And we're only doing it in 2 dimensions here, one spatial dimension, one time dimension, just to make some basic points before we go further. So we notice that we have increasing time going up the page, decreasing the past going down, and to the right, positive direction, to the left, negative direction. So the origin here is the present, they're here and now. Okay, next bit. We have on this diagram a globally defined vector fields, because if we look at all these vertical lines here, they are the coordinate curves. Okay, and we have tangent to these coordinate curves, and we have these vector fields. So all along here, for instance, we have the coordinate curve for the x direction, and we have the coordinate curve going up the page for the time direction. Tangent to these coordinate curves are our vectors. And this, for Minkowski spacetime, these are globally defined vector fields. For a general curved manifold, that's not the case. No such thing as a globally defined vector field. But in flat Minkowski space, where everything is the same everywhere, there is no curvature, it's flat. Then you have globally defined vector fields in the time direction and in each of the spatial directions. Okay, and these vectors point in the direction of increasing time and increasing spatial coordinate. Okay, and they are tangent to these coordinate curves. Okay, so along this blue vector is pointing this particular coordinate curve. Now where I'm moving my cursor along here, x is increasing in this direction. Okay, and tangent to that curve is this basis vector here, ex. Okay, and tangent to the vertical lines here, the coordinate curves in the time direction, is this tangent vector here, et, and it points in the direction of increasing time. Okay, so there we go. So we've got the coordinate curves here, and we have the tangents to those, okay, which gives us, in this case, Minkowski space, a globally defined vector field. Everywhere the same for each of the coordinate vector fields. Alright, now, the second postulate of special relativity says that the speed of light in free space has the same value of c in all inertial frames of reference. So all observers in constant relative motion with respect to each other agree on the value of the speed of light. And we can write this as dx dt as plus or minus c, okay, or dx on 1 on c times dx dt is plus or minus 1. So light travels along these diagonal lines. Okay, in Minkowski space, light travels along these diagonal lines. So any point you like on this diagram, draw out your diagonal lines, 45-degree lines, and they are the paths taken by light at that particular point. Okay, we can express that as a general relation here, anti-differentiate both sides of this first equation, putting in plus or minus c here, dt, we'll get x equals ct plus k. If we take here at x equals 0, x is equal to 0, at t equals 0, then we get rid of the constant k, and we have the lines given by the equation ct as plus or minus x. Alright, so they define the paths followed by light. These are null curves, and we'll see why shortly. Anyway, so plus or minus x is ct, writing it another way. Let's convert now, instead of just a single coordinate, let's look at a coordinate interval. So we have delta x is c times delta t, square both sides, and subtract the term on the right there, and we have delta x squared minus c delta t all squared is 0. Okay, that we will give now a special name, a space-time interval. Now for light, in this case we've been dealing with the yellow lines, the lines on which light travels, these 45-degree diagonals. The space-time interval for light is 0. In other cases it has a different value. Okay, so we say that light-like or null paths, delta S squared is 0, so delta S squared is the space-time interval, and it's equal to minus c delta t squared, this bit here, plus delta x squared here. And as we've seen for light, it's equal to 0, so light-like or null-like, light-like or just simply null, delta S squared is 0, time-like, delta S squared is less than 0, space-like, delta S squared is greater than 0. Okay. I just thought of a point, but I'll pick up later on. Okay, so let's have a look at how we use this. Let's just say we have some observer, he or she. Here they are standing at the origin, the clock starts ticking. 4 seconds later, they haven't moved from their location, but they have moved in time. So on a space-time diagram, we are always moving. We're never stationary because of the time component. So this observer, he, she, is standing at the origin here, in the here now, t equals 0. 4 seconds later on the space-time diagram, they are up here. Okay, they have a new location, 4C000. So this 4 vector here expresses the location. All right, we can now look at that in terms of their space-time interval. Delta S squared is minus c minus, in brackets, parentheses, c times delta t all squared plus delta x squared. And we see that that's minus 4c all squared plus 0 squared, because spatially they've not moved in their reference frame. So that's 0, and we end up with minus 16c squared. So that's a use of the space-time interval, and we're going to take that a little bit further shortly. Okay, now we have a second observer who passes the first. So our first observer is in frame S, standing stationary at the origin for 4 seconds. A second observer in frame S prime, if you like, passes the first in frame S with relative velocity of v of 4c on 9, and their respective origins briefly coincide, instantaneously coincide at t equals 0, so they share a common origin at t equals 0 for both clocks, and they can, in that instant there, calibrate their clocks, so they both agree with each other, both agree at t equals 0. Okay, as frame S passes with constant velocity v in the x direction only here, since we're only dealing with one spatial dimension, v equals 4c on 9. So gamma factor is 1 on square root of 1 minus v on c all squared, is 1 on 1 minus 4 on 9 all squared, is 9 on square root of 65. However, in frame S, the stationary observer, our first observer, they didn't move anywhere. Their net displacement delta x was 0, but their displacement in time was 4c. Okay, so, but for the second observer, their measurements of spatial and time intervals, because they're in relative motion, will be different. Okay, they will be different, and when we use the relevant Lorentz transformations, we see that in the primed frame, S prime, the second observer, their time interval, c times delta t prime. Notice I've been using, instead of just t on the time axis, I've scaled it to ct. That gives us both common units in the c times t as a unit of distance, and that then we can compare it with the x, y, and z directions, which are also in meters at a distance unit. Okay, so it's just a scaling of the time axis, nothing more. We get c times delta t prime is gamma times c times delta t minus vx delta x on c. Now delta x and delta t are in the unprimed S frame. Okay. Now for the observer in the S frame, delta t was 4c, delta x was 0. Okay. So, but in the primed frame, c times delta t prime, they end up with a result 36 on square root 65 c is approximately 4.47 c, whereas our observer in S recorded a time interval of 4c. Okay, this one has an interval of 4.47 c. Delta x prime for the observer in S prime is going to be different. Remember, delta x was 0 in this frame here because the first observer didn't move, so that's 0. But for but in the primed frame, that observer records an interval, a spatial interval of minus 16 on square root 65 c is approximately minus 1.98 c. Okay, now, but watch what happens. Okay, so just on a space-time diagram here, the red represents the S primed frame, the red grid here. You have the yellow diagonal lines. Okay, here's our first observer here in red. Okay, now the blue lightly print on the back there, dotted lines on the back, represents the primed frame. So X and T represent the S frame, measurements in the S frame. X prime, T prime represents measurements in the primed frame. And highlighting the primed frame by darkening the grid color, dotted grid here, we see that we have an interval here, spatial interval here, and we have a time interval here. So this blue axis here is X prime, and along this axis here, this is the time axis for the primed frame. Okay, there's been a rotation in here. Okay, which I'm not going to get into now, but the faster the relative speed between the two frames, the more these two blue coordinate axes close up, and the more this grid becomes elongated or stretched diagonally. So the two observers disagree on time intervals and spatial intervals, okay, but they both agree on the one thing that connects them, and that is the speed of light is the same in both frames of reference. They both share this diagonal line here. Okay, and that has implications for the space-time interval. Okay, so the value of the space-time interval for the second observer, delta S prime, is minus C delta T prime all squared plus delta X prime all squared. Putting those numbers in, we come out with minus 16 C squared. Now that is exactly the same result as the unprimed observer in frame S got. Okay, so the space-time interval is an invariant quantity whose value both observers agree on. The observer in the prime frame, the observer in the unprimed frame, that's our first observer here and our second observer here, both agree on this space-time interval, because what's connecting it is that both observers agree on the value of the speed of light. All right, what they do differ on are the spatial intervals and time intervals. Now the Lorentz transformation ensures that no observers, we use the Lorentz transformation to transform coordinates from one frame to the other on the previous slide, can travel at or greater than the speed of light with respect to each other. That no observer, can travel at or greater than the speed of light with respect to others, okay? You can't substitute in a relative velocity of c and get a meaningful result out. You just get one on square root of 0. Which is undefined, and you certainly can't have speeds greater than that of light. Okay, now both observers can agree on what is physical reality, even though their respective measurements of time and length intervals do not agree with each other. But they can Lorentz transform from one frame to another and agree on what is physical reality. Okay, so if our first observer, that's the one standing still, is now moving in both space and time, but still has a space-time interval of minus 16 c squared, okay, so that could be any one of these red lines here. Okay, then the second observer moving with some velocity with respect to the first, whatever it will be, it doesn't matter, will still obtain the value of minus 16 c squared for his or her space-time interval as well. It's an invariant quantity, both observers in relative motion with respect to each other when looking at observing the same events. Okay, that's the first observer standing here, and then 4 seconds later here, both will agree on the space-time interval, and that connects the two. It's a Lorentz transformation that connects them, but that's based on the fact that the speed of light is the same for both observers. Okay, causal relationships cannot be altered by transformations between inertial frames. Okay, so if physically real processes happen in a certain order, they do so independent of the motion of the inertial observers, then we must accept that information cannot be conveyed faster than the speed of light. Okay, the Lorentz transformation has set an upper limit there. You can get arbitrarily close to c, but not at the speed c. No causally connected events can be space-like separated. So delta S squared must be less than 0, at least for the metric that I'm using, the metric signature, which I'll talk about shortly, that I'm using. Light follows paths that lie along the surface of the cone here. If I add a dimension, okay, so that's a great thing. So no causally connected events can be space-like separated. They all have to be null separated, that's delta S squared equals 0, or light-like, which is delta S squared less than 0, which I'll pick up shortly. Okay, let's just, before I was just looking at yellow lines at diagonals because I only had the X and T dimension showing. If I add another dimension now, we go from those little yellow triangles to these cones, okay? And light follows paths which lie on the surface of these cones. This is for 1 plus 2 dimensions, so 1 time direction, 2 spatial dimensions. In 3 dimensions, 3 spatial dimensions, we're going to have a sphere, light spreading out in a sphere. Okay, so light follows paths that lie on the surface of these cones. So wherever you pick the present, you can put it anywhere in your diagram you want, and you'll just create a new light cone. Okay, and we'll look more into these light cones as this video goes on. Okay, now we can model space-time with a Lorentzian manifold, which is a pair MG, M comma G. M is an n-dimensional smooth manifold, and G is a metric with Lorentzian signature 1, 3. That's 1 time and 3 space there. And what I mean by that is, in this case, it's going to be -1 for the time component, and then +1, +1, +1 for each of the spatial dimensions. Now, about half the textbooks in general relativity use this signature, and the other half use the other one, which is +1 here, and then minuses for all the spatial ones. You need to look carefully at the book you're using and check which convention they are using, so as not to get yourself confused. This metric G we're talking about here, so M is our manifold, space-time is our manifold. We expect it to be smooth, not no sharp angles on it, no sharp points and no missing points. The metric G associates with each point P belongs to the manifold, or P is an element of the manifold, so a point on the manifold, so a point in space-time. And it associates a scalar, this is the role of the metric, it associates a scalar that is formed from the vector product of 2 vectors V belonging to the tangent space TPM. Now that's the tangent space to the manifold M at the point P. So that's the tangent space, so vector space, to the manifold at the point P. And so G is the vector product of these that takes this vector product and returns a scalar. Okay, so we can write this G of V comma V, and the components of which are G mu nu, V nu, and the metric lowers one of those indices and converts it to the other, so that we end up with V mu, and you can commute that and get the same result. Okay, this is a scalar. All right, when we sum this out, one index up, the identical index down, we sum with the Einstein summation convention. This gives us a scalar, a one-dimensional scalar. Well, that's what a scalar is, one dimension. Dimension 0, sorry. This is a scalar. Now, for any P, point P belongs to the manifold, the vectors in the tangent space to the manifold at that point P can be classified according to the vectors are time-like, if the inner product, dot product, scalar product, using the vector here to contract, using the metric here, sorry, to contract the vectors to produce a scalar. If that scalar is less than 0, it's negative, then the vector V is time-like. If the inner product, scalar dot product, is 0, then it is light-like or null, and it's space-like if this inner product or dot product or scalar product is positive, greater than 0. Okay, let's talk about curves now. So we have a curve, and again I'm in 1 plus 2 dimensions with the Z dimension suppressed. We can write our curve gamma. Gamma is a vector which is a function of the parameter lambda, so we parameterize this curve in terms of some parameter lambda. If you're talking about a particle with mass, then proper time is the one to use. If you're talking about a massless particle, such as a photon, graviton, or something like that, then you can't use proper time for that. Proper time for a massless particle is 0. You use some other parameter lambda. So we can extend these ideas to smooth curves in space-time. So we're going to talk about time-like, space-like, and light-like curves. And we're going to do that based on their vectors. But anyway, first let me start with a curve. So we can write a curve gamma as such that it maps the open interval AB to the manifold where A and B belong to the reals. Now this is an open interval. You can have a closed interval, you could have a semi-closed interval, it just depends on what you want to do. But we'll take this curve as mapping some open interval, and this is the parameter lambda here, is defined for some interval from A to B, okay, belonging to the reals. Okay, see this lambda here from A to B, and it maps that interval A to B to the manifold. So we get this curve gamma on the manifold, as this blue one shows here in space-time. At each point P belongs to the manifold on the curve gamma, we can associate a tangent vector, gamma prime, gamma dash, however you want to call it, which is the derivative of gamma with respect to whatever parameter you're using, lambda in this case. So gamma prime belongs to the tangent space to the manifold at the point P. So at each point P, you have a different tangent space, okay? And you have a different tangent vector because the vectors belong in different vector spaces. So gamma prime belongs to the tangent space to the manifold at that point P, so at each point P. Now, these curves can be classified according to their tangent vector. So this curve here, okay, is it time-like? Is it light-like or null? Or is it space-like? Well, what we do is we look at the tangent vector, okay? So gamma, the curve gamma, is time-like if its tangent vector, that's d gamma, d lambda, the derivative of gamma with respect to lambda. Each of the components are differentiated in that way. Of the 4 vector here, differentiate with respect to lambda. So gamma prime of lambda is time-like for all lambda belongs to that open interval AB. Okay, so this curve is time-like if its tangent vector is time-like for all the lambda on that curve. Okay, it's light-like or null if it's gamma prime, its tangent vector, the derivative of gamma, the tangent vector, is light-like or null for all lambda, again, belonging to the open interval. And it's space-like if the derivative of gamma prime of lambda, is space-like for all lambda belongs to AB. Now, when we say time-like, what we're talking about is taking the inner product with the metric, so contracting the vector with itself, and producing a scalar which is less than 0. Okay, a negative scalar value, and that tells us it's time-like for the metric signature I'm using in this video. And on this channel, I just use the -1, +1, +1, +1 signature. All right. Now, a curve gamma is causal if its tangent vector, gamma prime, gamma dash of lambda, is time-like or light-like or null. Light-like meaning null. For all lambda belongs to the open interval AB. Now, all particles follow world lines that are causal curves. Okay, nothing can move faster than the speed of light. All right, and particles with mass must move at less than the speed of light. Okay, so they're confined within that cone. Okay, so this blue curve here must lie entirely within the cone. Light itself travels on the surface of the cone, but a particle with mass must travel, its world line must lie within that light cone here. It can't travel as fast as the speed of light. Okay, so that makes these causal curves. Okay, so all particles follow world lines that are causal curves. Particles with mass follow world lines that are time-like causal curves. These world lines might well just be geodesics as well, but a spaceship with its own engine can direct its own path, and so it's not freely falling in space-time, and so it's not following a geodesic. Light follows geodesics always, so its world line is a geodesic. So massless particles follow world lines or geodesics that are null curves. Geodesics can be light-like, as I was pointing out here, for particles with mass. Okay. probably maybe tidy that sentence up because I really mean massless particles follow null curves. All right. Now, at each point P belongs to the manifold, the tangent space at that point P to the manifold, TPM, at that point is isomorphic to Minkowski space-time. So at each point on the manifold P, locally to that point, in that tangent space there, space-time approximates Minkowski space-time. Okay, or isomorphic to its at that point, strictly speaking, at that point. If you start to move away from that point, you begin to need to take into account curvature. Now, if you look at the surface of the Earth, globally, the Earth is almost a sphere, slightly oblate, but almost a sphere. It's clearly curved, clearly. But if you're looking from the point of view of your suburb, you're looking around at your shopping centre and your roads, it appears very flat. So locally it's flat. So at that point where you're standing, it's isomorphic to Minkowski space-time. Special relativity applies in your local environment. But if you start to move greater distance across the surface of the Earth, curvature becomes an issue and you must take that into account. But locally, just at your local point, and very local to you, it appears isomorphic to Minkowski space-time. And so special relativity is a good, excellent approximation at your point, okay? And that's what we mean by that. So you can, if you have a look at a whole definition of manifolds and so on, you look at mapping from the manifold to Euclidean space plus time, okay, and you can do that map. So we can say that at that point, the manifold is isomorphic to Minkowski space-time. All right, now the light cone at each point P belongs to the manifold, or P is an element of the manifold, is a subset of the tangent space of the manifold at the point P and not M. So the light cone, when we look at your local light cone, you're standing in your suburb, your local light cone, okay, relative to you, you don't have to worry about the curvature of the universe, curvature of the galaxy, curvature of the Earth, and so on like that. Locally to you, your space-time appears flat. So your local light cone, right, is a subset of the tangent space to the manifold at point P and not a subset of the manifold itself. Okay. Okay, so what that means now, we have two disjoint open sets of time-like vectors with one future-pointing light cone, VP, and the other a past-pointing light cone, VP minus. VP plus, so P stands for the point you're at, so at your point, so the suburb you're standing in right now, your light cone, light travels at 45 degrees from your point there. If you have a look, here's your space-time diagram. You're right at the origin here, okay? You know that in your XY direction and in the time direction, this is what your local light cone looks like, okay? And each point P, move to a different point, you're going to have a different set of light cones, okay? All right, so because you'll be in a different vector space. But locally, at that one point, your space-time looks Minkowski, light travels on the surface of these cones, okay? Particles with mass must travel less than that speed, so it travels within that cone, hence these blue lines are always within the future light cone or the past light cone, wherever. So pick any point on the curve here, put your local light cones in, and this blue line will lie in both above the point P, it will lie in the future light cone, below the point P, it will lie in the past light cone, not outside the cone, okay? So we have two disjoint sets. So our future light cone will be V plus, and our past light cone will be V minus at each point P. All right? Okay. Now the light cone at each point P belongs to M is a subset of the tangent space at that point. And you have different tangent spaces at each point. And tangent space, where all your vectors reside in the tangent space. Right, surface of the cones are formed. The surface of the cones are formed by null curves and null vectors. Now, Lorentzian manifold Mg is time orientable. Now, think back to the very first slide here. We had our space-time diagram. We had up the pages the positive increasing future time, and below was past. Negative was the past. Now, is time orientable if there exists a smooth, non-vanishing time-like vector field? Okay, so that at each point we can assign a future light cone and a past light cone. Okay, so at each point. Now, a space-time MG is then a connected time-oriented Lorentzian manifold if it has all those. Okay, so we need this smooth, non-vanishing time-like vector field at each point. Okay, and it needs to be connected. We can't have any holes in the manifold, can't have space-time missing a point, and no sharp turns either. Okay, no sharp bends. Right, now I'm going to invent some time-like field just for argument's sake, but let's say let T be some time-like vector field. Remember, if you think back to the second slide in the video here, we had ET. Here was our vector in the time direction, so this T is just the same thing. Okay, so we have some time-like vector field on M defining the future and past time direction. So remember, first and second slides here, up the page was future time, increasing towards the future, down was the past. Okay, remember the vectors, the time-like vector field everywhere pointed towards the future. Remember the little E subscript T, it all pointed up the page everywhere. All right, now here's a definition we're going to need for future videos, next couple of videos in this series. Given any non-zero causal vector v, so if we're talking about the fall velocity, we don't want something that's moving faster than the speed of light. Okay, we need something causal. Okay. So within a light cone. So given any non-zero causal vector v that belongs to the tangent space to the manifold at point P, so whichever point P you're talking about, the vector v is said to be future pointing towards the future, if the inner product, that's the contraction under the metric of the vector v with this time-like vector field we're talking about, this T vector that we've used to orient our imaginary manifold that we're talking about at the moment. If we then find the scalar product here, if we end up with a negative result here, when we contract it under the metric, then we have a future pointing, V is a future pointing vector, given that T has established the time orientation, okay, of our manifold, the time orientation of our on our manifold. So if this is negative, then we know that this is a future pointing vector. So this means the vector lies in the future light cone at the point P. Okay, by the same token, we say our vector belongs to the tangent space to M at the point P is past pointing, and so lies in the past light cone, V minus, if the inner product again with the same metric results in a positive result. Okay, so if this is positive, then we're going to have a past point, then V is past pointing. If this is negative, then V is future pointing. Okay, so just coming back to our first observer, if I come down here to, here's our vector V, this components V mu in terms of the basis E mu, we could write that as just components C0, 0, 0. Okay, this is our first observer. Okay, that's their fall velocity. Okay, we could write that as C times E basis vector T, okay, E subscript T. Our time oriented, our vector T, which gives us a time orientation, our manifold T, is T nu E nu. We can write that as C E T. We have to choose up, don't we? Because it's increasing time. It's in the positive direction, so we have to choose that to be our time orientation for our example here, for our manifold, which is Minkowski space-time. Our metric here, eta mu nu, because we're in Minkowski space, flat space, is diagonal minus 1, 1, minus 1, plus 1, plus 1, plus 1. So returning to our first observer from earlier, she has a position vector CT 0, 0, 0 and a fall velocity C 0, 0, 0. Okay, and the inner product there, contraction of V and T with our metric, gives us this object here. Okay, that gives us, okay, which is ET dot ETC squared is eta TT, because G mu nu in our case is eta mu nu. Contracting that, now that component there is -1, remember, for our down here, eta mu nu, the 0, 0 component, or TT component is -1. So minus c squared to less than 0. So clearly the observer's fall velocity is future pointing, because this result here was negative, less than 0 here. So it's a future pointing. So this vector here is future pointing, which is what we expect. We know that you can only go forwards in time. You can't go backwards in time. So clearly it's future pointing. The reason I bring all this up now is when I come to the curve geometry, we're going to find things called closed time-like curves. We'll see a different result happens there. Okay, now, let's a few definitions again. A causal time-like or null curve, gamma of lambda, the parameter is lambda, is said to be future pointing if gamma prime, that's the derivative of this vector with respect to the parameter lambda, is future pointing for all lambda. So a causal time-like or null curve is said to be future pointing, okay, if, is future pointing for all lambda, i.e. at every point along the curve, if the contraction with the metric of gamma prime with t is less than 0. Okay, so that scalar result here will give us a negative result. So then we say that this is future pointing. So clearly gamma prime here is future pointing. Okay, here's our curve gamma. Another definition, the chronological future of the point P belongs to M. Okay, anywhere along here, pick a point P, belongs to M, then its chronological future, the set of points in its future, I plus, is a set of events that can be reached by a future directed time-like curve starting from P. Okay, this is a time-like curve starting from P. Okay, IP is a set of events that can be reached from P using a time-like curve. If there is a future pointing time-like curve in M from P to Q, okay, so pick a point P and then there's some curve going to Q, then we denote this as P double less than Q. Okay, and the chronological future of the point P, I plus, is the set of points Q belong to M such that P double less than Q. Okay, so it's all the points that can be reached by a time-like future pointing curve. Okay, the causal future of point P belongs to M. Okay, some point P, it's chronological, it's causal future now. Okay, now this is going to be an expanded definition over the I plus, is denoted by J plus of P. So that's all the points in the causal future of J. It's a set of events that can be reached by a future directed causal curve starting from P. Now that means it can be a time-like curve or it can be a light-like or null curve. Remember, the chronological future was about time-like curves, but now causal is about time-like and light-like or null curves. Okay, and that's J plus. Okay, if there is a future pointing causal curve in M from P to Q, okay, so time-like or light-like or null, light-like and null being the same, then we denote this as P less than Q. Also, P is equal to or less than Q means P equals Q, so P and Q are the same point, or P is less than Q, so you can go from P to Q. So J plus of P, it's a set of points in the causal future of point P, J plus, is a set of Q belongs to M such that P is equal to or less than Q. Now the chronological and causal pasts are similarly defined. So instead of future directed curves, okay, with the tangent vector being the inner product of the tangent vector with the time direction vector being negative, now you want it to be positive because you want past directed curves, okay? Past directed light-like curves or past directed time-like curves, but it's the same. You just put, instead of J plus, you have J minus. Instead of I plus, you have I minus. Same definition, but just past directed in both cases. So you just swap the words past directed. All right, now the line element in flat Minkowski space-time with coordinates ct, xyz is ds squared is eta mu nu dx mu dx nu. It's this object here, expanding it out. The line element in curved space-time with generalized coordinates x mu, and the four coordinates here is ds squared is g mu nu dx mu dx nu. In either case, flat or curved space, time-like ds squared is less than 0. Light-like ds squared is 0, or null ds squared is 0. Space-like ds squared is greater than 0. Okay, and I believe, have I got to the end? Yes, I've got to the end.